What exactly is an IPv4 address? How does it work? What is this thing called a subnet mask? And what about the future of the IP protocol addressing? What is an IPv6 address? How does it differ from the IPv4 address? All of these questions and more will be answered in this important live lesson dealing with v4 and v6 addresses. This is a critical live lesson for anyone wanting to do anything involving network support or implementation in a modern day networking environment. I hope you'll join us for this live lesson where we examine in great detail the v4 and v6 addresses that are critical in networks today. Welcome back, everyone. It's now time for us to discuss none other than IPv4 and IPv6 addresses. Back when we were discussing the OSI model, we said there was that internet layer or network layer, depending on whether we were discussing the OSI model or the TCP/IP model. We would call it OSI would be network, of course. The TCP/IP model would call it internet. This important layer is going to contain these IP addresses, either IPv4 or IPv6 addresses. Let's go ahead right now and take an in-depth look at both of these styles of addresses. And we begin with the logical question of why do we even need them? Well, we need a way in which we can uniquely identify devices on the network, and these addresses are going to enable us to do this. These addresses are what we call hierarchical. You know, it took me a long time in my networking career before I could say hierarchical. That was very difficult for me. But what we mean by hierarchical is they are in sections. Each portion of the address represents something. So when you look here and you see the IPv4 address, you see that a portion represents the network that we live on, we typically say, that our host machine is plugged into, and then we have a host portion. And the host portion of the address identifies a particular workstation on that network. A great analogy for this is like your street and home address. We have a street address like Main Street, and then we have a street number that we live on, like 101. So 101 Main Street is a great analogy for the hierarchical nature of these IPv4 addresses and how they describe where a particular workstation exists. Now, when you look at the IPv4 address, we discover that it is made up of 32 bits. And we break up these 32 bits into 4 octets. We call it an octet because it contains 8 bits. Look at that. So we see an address for human readability. We use what is called dotted decimal notation to represent the IPv4 address. But the computer doesn't see it this way. The computer sees 32 bits. In fact, the computer doesn't even break them into octets. It just sees them as one continuous string. So pretty amazing the difference between how we see the address and how the computer sees the address. Now, when the computer displays them to us, it of course utilizes the dotted decimal notation. Let's go ahead and take a look at that. If I bring up my command prompt, so we're on a Windows machine right now, and we bring up this nice command prompt, and we use that ipconfig command, the computer says, okay, you are using an Ethernet adapter to connect to the network, and your IP address is, and look at this, they give it to us in that nice dotted decimal notation. You can see that we are 192.168.1.7. So wonderful. We get a nice display from the network machine in a readable fashion instead of that string of 32 bits. Well, something else that we need to understand about IPv4 addresses is that they are classically classified in what we call classes. That's right. We have a Class A Class B, and a Class C network address space that was initially defined. There is indeed Class D not shown here. That is for something we call multicasting, and we'll cover that later on in these videos. And then there's a Class E we won't cover at all. It was addressing reserved, set aside for experimental purposes. Now, there's lots of memorization you need to do in here, so I highly recommend you use flashcards in order to repetitively practice this information and memorize it. Notice that with a Class A, the first octet identifies the network, so the first 8 bits, and then the last 24 bits identify the host. When you work out the mathematics on this structure, and in fact, the first couple of bits in each of the A, B, and C are going to be preset to certain values. For instance, the first bit in a Class A is going to be preset to a 0. So what you're going to end up with is in a Class A, the first octet will be in decimal, so you can recognize it, from 1 to 126. That's right. So if we see an address like 9999, we know that classically that is categorized as a Class A network. Pretty cool. Class A network, 8 bits for a Class A IP address, 8 bits for the network identification, 24 bits for the host identification. This means we can identify relatively few networks, but each of those networks can have many, many host addresses. Exactly how many? We'll see that later on in these series of videos. A Class B address. It has 128, 191 in that first octet, and it has network, host. 16 bits for network identification, 16 bits for the host identification. And then finally, the Class C. We have network, host. That's 24 bits for network addressing and just the 8 bits for host addressing. And the first octet will fall 192 to 223. Lots of memorization here. And again, I recommend you use flashcards. Also, bring this to life by going to a machine, looking at an address like 192.168.1.7 as we see here, and realizing, oh, wow, cool. I have a Class C address. Pretty awesome. Okay, now, the people that invented this technology for us and regulate this technology for us, they did a pretty neat thing. When they realized that they were running out of these IPv4 addresses, they did a neat thing. They said, you know what? We'll go ahead and take some of the addresses that we had leased out to organizations, and we'll reclaim that space from them. We'll find out who can surrender some. So they grabbed some of the space back, and they made it private space. I want you to memorize these addresses. Again, great place for your flashcards, right? These private addresses are for use as many times as we want inside private organizations, like your home or your company. That's right. You and all of your friends can, inside the privacy of your own home, use these addresses all you want. A router that's connected to the internet knows not to route these out onto the internet. Pretty cool. And what your home internet service provider will do, for instance, is they will translate this address. They won't route it onto the internet. They'll translate it into an address that can be used on the internet. This is called network address translation, and it's something we'll discuss later on in the videos as well. So these are your private addresses. We have the 10.x space, so all of the 10 whatever space is reserved. 172.16 to 172.31 and 192.168 is reserved. Aha! Look back at my home IP address here. Sure enough, it's a 192.168. That's because I'm behind my home ISP router, and sure enough, I'm using private IP addressing. So, very important that we understand that some of the IPv4 address space is private use only, and this was a great band-aid for fixing the IPv4 address shortage. But it was only a band-aid. And thanks to the popularity of things like mobile phones and other types of mobile devices, we are in a situation where we still need a lot more addresses. And that was the major catalyst for the creation of IPv6. With IPv6, they take the address space and they move it out from 32 bits to 128 bits. Wow. And no longer is there a dotted decimal notation, because that would still be too long. They use hexadecimal in order to represent the IPv6 address. So there you can see an IPv6 address in all of its glory, folks. Look at that. A nice long hexadecimal string that represents the address. Did this solve the shortage? You better believe it solved the shortage. As a matter of fact, for now it did at least, with the 32-bit address structure, there was 1 billion plus addresses possible, right? We're in the billions with the number of addresses we could have, and we quickly used those up. With the IPv6 address, it's an amazingly large address space. There's billions and billions and billions of addresses available for every square inch of the Earth's surface. Yeah, it's amazing. Exponential mathematics. When we go from 32 bits to 128 bits, it is truly amazing how many addresses that we can create. Now, let me show you a neat trick we can do with our IPv6 addresses, because you notice they're still kind of long and cumbersome, even though they used the hexadecimal representation. Here I'm going to a Cisco router. It doesn't matter that it's a Cisco router. It just happens to be. It could be anybody's router. And I'm going to go into an interface, and I'm going to say IPv6 address. And then what I'm going to do is I'm going to input the IPv6 address under this interface, but I'll show you some neat things, some neat shortcuts. Let's say it's 2001, and you'll see this address a lot. That is one of the address spaces that they've released for us to use with IPv6. And then let's say we have 1111, and then let's say we have a whole bunch of fields with just zeros in them. Well, there's a neat trick. Exactly once in an address, we can go in and we can represent all of those fields of zeros with a double colon. That's right, colon, colon will represent all of those zeros. How neat. And then there's another trick we can do. Anytime we have leading zeros in a field, we can go in and we can trim the leading zeros. You can do that as many times as you want. So 2 nifty tricks to shorten those IPv6 addresses. All groups of zeros once in an address can be represented as colon, colon, and then finally in any field we can trim those leading zeros. Now the last thing I wanted to talk to you about in this particular presentation, other than these IPv6 addressing shortcuts that we just looked at, is indeed the different IPv6 addressing types. Later on in our series of videos, we'll teach you all about multicast, which is sending traffic to a group of receivers instead of the traditional unicast, where you send traffic to exactly one workstation on the network. IPv6 fully implements something that was experimented with in IPv4 in addition to the 2 classic forms, and it's called Anycast. And what's so neat about Anycast is the workstations will have the exact same IPv6 address, and we will send to that address, and whoever is closest will respond. Closest can be determined through a variety of factors that you can literally configure. So it's a pretty neat way to add high availability to your infrastructure. Just address everybody the same, and then go ahead and send traffic to whoever is deemed closest by the network devices. So, IPv6, it's going to dramatically improve the number of addresses that are available, but it's also going to bring other improvements as well. In fact, there is one more that I want to show you. It has this link local address that it uses, and that's at FE80. In other words, when you see an IPv6 address that begins with FE80, this is an address that is used just for communications on the local link. How clever. So anytime you just go and turn on IPv6 on one interface that's connected to another interface and you turn on IPv6, the machines can automatically communicate with each other because of these link local addresses. It's kind of similar to the automatic private IP addressing that happens on Microsoft Windows systems. But just keep in mind that there's lots of enhanced, new and exciting features to IPv6. One mistake we tend to make regarding IPv6 is that we think about it just in terms of the increased address space, but we don't stop and think about and study all of the great enhancements that we're going to get with the IPv6 protocol. And there are just enhancement after enhancement. It's better for mobile devices. It has better built-in security. It has a much easier auto configuration if we wanted to eliminate DHCP from our network for the assignment of the address. All kinds of great features with this exciting new protocol. Well, thank you so much, everyone, for your attendance in this Network Plus video, where we took a look at IPv4 and IPv6 addresses.